Hey, Chem kids. Now we're going to talk about cool covalent bodacious bonding. All right, let's see. Our essential questions now are: what types of elements get involved in covalent bonds? What are molecules and how do they form? What types of molecules even have to do with covalent bonding? Well, we are about to find out. All right, so quick review. A metal and a non-metal will transfer electrons. You are familiar with this? What is this? An ionic bond. Okay. Metal ions mix in a sea of electrons. What do we call this? A metallic bond. So there's one more type of bond that we need to learn about, and that is when we have two non-metals. Actually, it can be more than two. We're going to be working mostly with what we call binary compounds. Neither one of these are going to give away an electron, right? There's not extras in the case of nonmetals. They are all just craving, bringing in just one or two or three more electrons. So they're not going to give them to each other. They end up, what we say that they share their valence electrons. That's one of the words that we use for it. There's a more accurate way of describing it that we'll talk about later. But for now, we're going to just use that language, that they share their electrons in order to have everyone in the situation feel like they have a full shell. And that is a covalent bond. Okay, let's see. So we know that nonmetals hold on to their valence electrons. They're not trying to give them up. They're trying to bring in a couple more. They're not going to give away electrons, but they still, of course, want a full valence shell. That's every atom's mission in life, to fill that shell. So they get it by sharing their electrons with each other. So think about the root of that word covalent, right? Valent is going to be the valence electrons. And co, what does co mean? What does that mean as a prefix? Hopefully you're thinking about things like cooperate, community. Those are the ones I can think of right now. It means together. Co means together. So they put their valence electrons together and use them together so that everybody gets to use some of the same valence electrons to have that full shell. Okay, both atoms, in the case of binary covalent compounds, both atoms get to count the electrons towards that noble gas configuration. Remember that feeling of having a full shell. All right, let's see, what else have we got? When we are talking about covalent compounds, that's when the word molecules becomes an accurate term. Okay, so it is specific atoms that are joined together because they are sharing the same set of electrons. We talked about the fact that in an ionic compound, we don't have molecules. Okay, we call those like a salt crystal. And it's, the formula is that smallest ratio of however many cations you have to however many anions. But with covalent bonding, it's a specific number and type of atom. There are two types of molecules that we need to talk about. One of them is a molecular compound, right? That's pretty straightforward. When you have different elements that come together, atoms of different elements that come together and create a covalent bond, that's a molecular compound. Here's the one that we need to know about, that this might be new to you. The ones that are called diatomic molecules. So atomic, of course, means having to do with atoms. That prefix di, that means two. All right. So when you have a diatomic molecule, that is two of the same atom bonded together. We don't call it a compound because it is not more than one element. It's just an element, but it's an element that has two atoms in a molecule. Okay, so for example, O2 is oxygen gas, N2 is nitrogen gas. These are the things that make up the majority of the air. Okay, it's not oxygen by itself. It's not a single oxygen atom floating around in the air. Okay, all of the oxygen that is in the air is O2. All of the nitrogen that is in the air is N2. All right, these are not compounds. Again, it's only one element. So there are 8 elements on the periodic table that always form diatomic molecules in the absence of anyone else to bond with. Okay, so these 8 elements you are never going to find as singular atoms in nature. That's what we mean by that. They always form diatomic molecules. That's not to say that they won't get involved in other bonds with other atoms and get involved in compounds. But when there's no one else for them to bond with, they will bond with each other. Those 8 atoms are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine, and astatine. All right. So for example, when in your everyday life you hear someone talking about oxygen, the oxygen in the air, I'm breathing oxygen, my grandpa's on oxygen, okay? When we say that, we mean O2. We're talking about oxygen gas, okay? Now, sometimes in chemistry class, or a lot of times in chemistry class, when we say oxygen, we are talking about oxygen, an oxygen atom by itself. Okay, like if we're talking about H2O, we'll talk about the oxygen in H2O, and that does mean that single oxygen that's in that molecule. But generally speaking, when you hear someone talking about oxygen, they mean oxygen gas with a formula of O2. It's 2 oxygen atoms bonded together covalently. All right, so maybe if you look at this list, you might notice that it is the gens, hydrogen, nitrogen, oxygen, enes, right? These are all the, well, it's funny because also the halogens, right? Fluorine, chlorine, bromine, etc. One way to remember this is that they make a 1+7 pattern on the periodic table, right? There are 8 of them. And so we can look at what that looks like in a moment. I'll have a little graphic representation for you. Other funny little mnemonic for this is Brinkelhoff. I always think of, oh, Dr. Brinkelhoff, the beloved chemistry teacher. I don't know who that is. But if you look, right, it would be pronounced Brinkelhoff. But it's Br for bromine, I for iodine, N for nitrogen, Cl for chlorine, H for hydrogen, O for oxygen, and F for fluorine. Obviously, astatine is not in here. Maybe his first and middle names start with A and T. I don't know, old Dr. Brinkelhoff. Astatine is less common. You're not going to see it as often, so it's not one to worry about as much. But all of these, you definitely want to recognize that if you have that element by itself, it's going to have a formula of like 2, whatever the symbol is, 2 with a subscript of 2. Here's that 1+7 pattern, right? Hydrogen over here all by itself. And then the 7 is the nitrogen, oxygen, and fluorine, and the rest of the halogens. Okay, so if you're more of a visual learner and glancing at the periodic table and going, oh, okay, it's that one and these 7, then that's a good way to remember it. I tend to think about Dr. Brinkelhoff. All right. I think we're going to keep going. Let me see. Yeah, we'll keep going. Let's go ahead and talk about the properties of molecular compounds. As we know, these are made of non-metals, okay? Typically, you're not going to have metals involved in covalent bonds, okay? And remember, that's what we mean when we say molecular. They're covalent. It's really saying the same thing to say molecular compound or covalent compound. And there are many, many, many different combinations, okay? So the molecular formula, you're familiar with this. We've talked about molecular formulas before when we talked about counting particles, right? A molecular formula shows the type and number of atoms, of specific atoms in a molecule. So it's not necessarily the lowest ratio like we do with ionic compounds, right? We don't say that magnesium oxide is Mg2O2, right? It's just a 1-to-1 ratio for those. So we just say MgO. You can have as many of those as you happen to have in your crystal, and the formula is that lowest ratio. Not so for molecules, okay? Remember our old buddy glucose, C6H12O6. There are actually 6 carbon atoms and 12 hydrogen atoms and 6 oxygen atoms in a glucose molecule. This whole thing is the molecule, okay? So we looked before at the empirical formula. The lowest ratio for this is CH2O. That's the empirical formula, but it is not the actual chemical formula for glucose, okay? These numbers are the chemical formula. All right, I'm going to try to wrap this up. Here are the properties, things that we need to know about molecular compounds and what they're like on a macro scale. Okay, these tend to be poor or non-conducting as a solid, a liquid, or an aqueous solution. Okay, they don't allow electrons to flow freely. The electrons are all involved in the bonds, so they're busy helping atoms feel like they have a full shell. So they're not going to be free to flow around. Even as liquids, they're not going to do that. They're not going to allow for the flow of electrons. and in aqueous solution, typically, even if they are soluble, which sometimes they are and sometimes they're not usually going to allow for that flow of electrons. You saw that with aspirin, we know in your lab was it was kind of soluble. I mean, it dissolved a little bit, but it really didn't light up the light bulb, right? And wasn't conductive. Okay. These may or may not be soluble in water. Molecular compounds have many, many, many different kinds of properties. Okay. So it really depends on whether the molecule is polar or not. And we'll talk about what that means and the influence it has later. These do tend to have low melting and boiling points. In fact, many covalent compounds are gas or liquid at standard temperature and pressure. And the reason for this is that you only need to break the intermolecular forces, the forces that hold the molecules together. We've talked about that a little bit when we talked about changing phase, right? That there are forces that will hold molecules next to each other, either in a solid or even if they're flowing around each other like a liquid. That's the only force you need to break. And those are weaker than molecular forces. Okay, so what we're really saying here is that covalent bonds themselves stay intact, right? When you melt water, well, you just have water molecules flowing around each other. Those water molecules have not changed. They're still water molecules. When you boil water, those water molecules have floated out into the air, but they're still water molecules. You don't have to break a covalent bond to melt or boil a covalent compound. That might be all we have for right now. Okay, so you will have a mastery check on Canvas for this stuff. So, make sure that you understand these pieces and then go ahead and try that mastery check.